Okay.
And then if you need a clicker.
Got it. Okay.
Today's MSNE seminar, we have the honor to have a renowned speaker in the field of thermal conductivity and in general the nanothermal, in the entire nanothermal area, Dr. David Cahill from the University of Illinois at Urbana-Champaign. David has been the department chair there for 8 years and just retired from his position and going back to his beloved lab. So he has developed this fascinating method called time domain thermal reflectors, TDTR, and that has led to a giant boost for nanothermal research in the past 20 years. So David has been obtaining a PhD in Cornell, right? Mm-hmm. And then directly, and then started your career directly in UIUC.
Yeah, I spent 2 years at IBM.
Oh, spent
yeah,
exactly.
Yeah.
So at IBM there was a fascinating interaction with a lot of people in the semiconductor industry. So with that, I will probably just directly give time to David.
Yeah, thank you. Really glad to be here. Thank you for hosting my visit. Yes, I stepped down from being department head about beginning of this calendar year, and I'm driving my students crazy. So I'm in the lab trying to fix get everything working the way I want it. It's been great. Okay, so I'm going to talk about problems in the thermal transport at the nanoscale, and I'm going to spend some time, defining all those things. Particularly this concept of problems. I'll at least touch on. Yes, I'm in the Material Science Department at the University of Illinois, affiliated with the Materials Research Labs, a wonderful institution that brings together a lot of the materials research community at Illinois into a common area with really beautiful facilities. I also have courtesy appointments with mechanical and sciences and engineering and physics. These are all the people in my group over the past, say, 10 years or so that have contributed to the topics that I'm going to talk about today. A lot of great people now off doing great things on their own at other places, and thanks to some funding. All right, so this is an outline of what I want to talk about today. I'm going to give you an introduction to the transport coefficients that I'm interested in, the transport coefficients for thermal sciences that we care about. And then I'm going to take a little bit of a digression and say something about from the big picture about how we're prioritizing our work. In other words, how am I picking what we work on? And I'm going to talk about this idea of, a puzzle versus a problem. Both are important. Today I want to focus on what I consider are important problems. And those problems are listed here. So I'm going to talk about how low can we go. So what is the lowest possible thermal conductivity that we can obtain in a dense space-filling arrangements of atoms. Talk about both inorganic materials and also polymeric and soft matter materials. I'll spend a little less time on this problem of heat conduction by spin waves. We normally think of heat being carried by phonons in insulators, electrons in metals, but anything that is thermally excited in a material that has a group velocity, that has a mean free path, can carry heat, and in certain compositions of copper oxides, those mechanisms can be extraordinarily large compared to other materials. I'll talk about that. And then I'll finish up with something that's a little closer to maybe to engineering about how do we find materials that have greater, I call thermal function. So instead of just having a static property for a thermal conductivity that you could look up in a handbook, materials that can respond in some way to their environment or to applied driving forces that can give me something more to do, like creating a thermal switch or a thermal regulator. All right, so these are the transport coefficients that I'm interested in every day in the lab. This is what this is our bread and butter. This is what we go in the lab and we measure. The first is the thermal conductivity. I'm going to write that as a capital lambda. And that's something that everyone learned about in freshman physics classes. You learned Fourier's law, that's this. So the heat current is equal to minus the thermal conductivity times the temperature gradient. It's a property sort of continuum. That's the level that we're going to talk about that here today. Or I can talk about another transport coefficient that's important to us is the thermal conductance per unit area. We write that as a capital G. That's the property of an interface. That's not something you heard about in freshman physics, but it's very similar. It's just a linear transport coefficient that relates a heat flux crossing an interface to the temperature drop across the interface. Okay, these are kind of macroscopic definitions. If you care about microscopic details, then those are sort of whole other talks. There's a whole other discipline to worry about that. And I'm also just sort of highlighting here that since these are linear transport coefficients, I can always write a dissipation fluctuation theorem for that property that Einstein showed us how to do so many years ago. And these are just the sort of fluctuation forms of these transport coefficients. Another way of thinking about the transport coefficient. Now, why do we care? Well, mostly we care because thermal conductivity, interface thermal conductance are properties that we need to be able to put into, say, some sort of modeling software that we want to predict what the temperature field would look like in some device or in some structure. Typically, this sort of interfacial thermal conductance problem is not really that important unless you move very down into the nanoscale or are working with very high thermal conductivity structures, but it's certainly one of those things. Okay, so thermal conductivity is important because, well, that's what appears in the heat diffusion equation. My favorite differential equation, which it has in it the heat capacity per unit volume and the thermal conductivity Laplacian of temperature and one derivative of temperature with respect to time. I can also talk about the ratio of those two. That's the diffusivity. I can take the product and take the square root. That's the effusivity. You're probably familiar with diffusivity, has the same units as mass diffusion, length squared per time. Effusivity has weird units, but it's actually not very intuitive. But effusivity is something you're very familiar with. If you put your finger on something that's, I don't know, kind of metallic and it feels kind of cold, that's because that material has a high effusivity and it's good at pulling heat away from your hot finger, and you feel that as a sensation of cold, even though it's the same temperature as other things in the room. That's the one-dimensional flow of heat is governed by the effusivity. This is the interface conductance. That's a radiative boundary condition on the temperature. This is basically the same equation I wrote on the previous slide. This is the heat current in the material. This is the temperature drop. That's the interface conductance. And sometimes we like to think about this term as the ratio of these. So I take thermal conductivity divided by thermal conductance of interface. That has units of a length. That length is given the name Kapitsa length in the literature, and that's in honor of a Russian scientist, Nobel Prize winner also, Kapitsa, who studied liquid helium, various aspects of liquid helium, but in this context, he was the first person to study this problem quantitatively, and it was for between copper and liquid helium. So what was the thermal resistance at that interface, which is actually substantial and is important in cryogenic material designs. All right, so thermal conductivity of dense solids. And what I mean by dense, again, I'll just define that and I'll put it aside, but dense means kind of space-filling arrangements of atoms. So no fair putting pores in the material. I'm thinking about dense solids. And right now that range is about 40,000 at room temperature. We've succeeded in my group and others, pushing the lower limit down. I'll talk about that, quite extensively. No one's really found too much of a way to go up. So the thermal conductivity of diamond is the highest thermal conductivity. I think graphene maybe is a little controversial, what exactly its value is at room temperature. It's not clear that it's much higher than that. But diamond has a very high thermal conductivity. The heat's carried by phonons, wave-like lattice vibrations. They have a high velocity. They have a high coherence. So they have a long mean free path. So they're very efficient at carrying heat. Copper has the highest, well, close to the highest thermal conductivity for metals, and that's because the mobility of the electrons in copper, silver, gold is very high. The density, the heat capacity of the electronic system is large, and so again, it's a good conductor of heat, but in that case, due to electrons. So those are the usually main carriers. And there's a few other interesting points on here. Like I said, I'm going to say a lot more about this bottom part later, so I won't talk about that here. But let's just kind of keep going down. Here's an interesting data point which comes from 2018. There were 3 papers in Science back to back, all reporting the thermal conductivity of the 3,5 zinc blende crystal boron arsenide, all grown by basically the same technique, all measured by the same basic technique, time domain thermal reflectance. And you might ask, why did that require 3 papers? And I would agree, but that's sort of a curious thing. But it's good to see everybody agreed, and we're all fine. And so we measure about 1,000 watt per meter Kelvin in this material, and I'll say more about that later. It's kind of a fun story. Silicon's about here. You know, that's the sort of $1 trillion material. Xylon is the highest thermal conductivity of an organic polymeric material that I would say is in some sense real. In other words, my definition in this case of a real real material is something like I can order from Amazon. And you can order from Amazon Xylon, I don't know, fishing string or bike spokes or something. And it's a liquid crystal polymer, and it has a thermal conductivity of about 20 watt per meter Kelvin at room temperature. That's similar to the thermal conductivity of a, say, stainless steel or metal alloy. And it's along the liquid crystal and ordering direction. So this is the highest of any organic solid. And then we go into amorphous materials. 1 is a good number to remember. That's basically window glass. Has a thermal conductivity of unity in watt per meter Kelvin. Polymers typically have about 0.2 or so. And like I said, I'll talk about these numbers down here, which are about 0.05. This is an organic material. This is an inorganic material. For completely different reasons, they have thermal conductivities of about 0.05 watt per meter Kelvin, which is about twice the thermal conductivity of air. Yep.
What is transporting heat in Xylon?
In Xylon, it's just vibrations of the molecules, right? So I would think of it as essentially acoustic phonons. Again, I would say we don't know very much. We don't know much about their dispersion. We don't know much about the scattering mechanisms. Yeah, we're kind of trying to renew that line of investigation and try to say more about those kinds of things. A lot to do, actually, in these. I find there's a lot to do in organic soft matter in general. In this subject. Okay, yeah, so this is this fun story about boron arsenide. So there are a couple points about this I want to leave you with. One is this, okay, this is a paper from 2013, but actually the whole subject starts somewhat before that, and it's really an impressive advance in theory. So theorists, by combining densely functional theory, so computational techniques, quantum mechanical based, to calculate the force constants of atoms, as well as their nonlinear force constants, so their anharmonicities, and then using that information to solve transport equations, Peierls-Boltzmann transport equation, which was first written down in the 30s, but had never been solved quantitatively until quite recently, can make predictions. So this is just one example. This is from David Broido, I think would be considered really the lead of this group. Predicted that this crystal boron arsenide would have a thermal conductivity at room temperature about the same as diamond, and above room temperature would exceed the thermal conductivity of diamond. Right? That's a wonderful thing for a theorist to do, predict something that we don't expect. We certainly didn't expect this, because on average, its acoustic phonons kind of look like the acoustic phonons in silicon. And the only difference is that the optical phonons are pushed up in frequency. That's the critical thing. And the fact that maybe some of these dispersions, the details of these dispersions are a little different. These things in silicon, it's much more spread out than it is in this boron arsenide. Anyway, so that was the prediction. Got a lot of people excited, got federal agencies writing checks. And so there was a MURI formed, and this multidisciplinary university research initiative group, got together and grew crystals and worked hard to make them better and better, do measurements, and then this was kind of the ultimate. This is the paper from my group. That's my student, Chia Zhang, in science. And so what we found is that the thermal conductivity in the best crystals have a thermal conductivity of about 1,000 watt per meter Kelvin at room temperature. Now remember, the prediction was diamond. The prediction was up here, and that's labeled with 3 phonons. So what that means is the original prediction was based on interactions of 3 phonons, so third order anharmonicity. Well, it turns out this isn't good enough. And the experiments then drove the theory people to go farther and include fourth order anharmonicities, 4 phonon interactions. And we're able to predict thermal conductivities that are quite well aligned with what we saw. And now we're going back to, working on seeing whether maybe some of the crystals could be a little higher, refining the theory in any way. It's a good interaction between theory driving experiment and then experiment driving theory to be better. And now I think we're trying to, both to be better again, as time goes forward. So these are the kind of crystals that are grown, a few hundred microns, but that's actually these days is quite easily measured in our experiments. Okay, so that's the introduction. Let me give you this little bit of a digression about what I wanted to talk about in terms of how we're prioritizing what we want to study and the kinds of topics I wanted to share with you today. And some of this goes back, to sort of philosophers of science, such as Kuhn, but let me just credit George Whitesides, who's a very accomplished chemist at Harvard, who I'd heard talk about these kinds of ideas, added some award, I think in 2012, but it actually goes back farther. And quick summary is this definition of these ideas of puzzles versus problems. So let's just start first by talking about puzzles. We'd say normal science, these kind of go back to Kuhn. So normal science is driven by puzzles, right? So this is mostly what we do in the lab every day. This is what we talk with our grad students and say, well, there's this kind of thing we don't really understand very well. Do some experiments, see if we can figure this out. Fill this gap a little bit, okay? Develop a scientific paradigm. Well, George Whitesides in this talk and in his writing, and I think, echoing maybe something, is maybe a little more critical of this, or how do we think about these things. So in a puzzle, he would say, well, that's something we already knew, really. The answer is not particularly important. The interest is mostly in the process of doing the work. So the sort of the process of the elegance of the solution is what this is. Okay, but absolutely essential. It's not to put this down. It's an essential part of what we do, but just be careful. We're distinguishing it. It's something different, maybe, than a problem, okay? So if we go on, we would say, okay, scientific discovery is driven by problems, and that really comes from Kuhn. So George Whitesides says, defines this as something, a larger scale question where the answer does matter, where maybe we don't even know how to get to the solution. We may not even know there is a solution, right? And these are problems in our scientific work. Right? So nanoscale thermal transport or thermal sciences, what are the problems that I consider when we're picking our work? Well, I'm going to talk about those today, some of them. How close can we approach the perfect thermal insulator? That's a big picture question. There's no fundamental limit that says it can't be 0. Well, there is kind of. It has to do with translational symmetry, and acoustic modes always have to be present, but it doesn't have a real limit. What are the upper and lower limits to the thermal conductivity of a polymer? Somewhat similar, but within a narrower group of class of materials. If I just give you carbon, nitrogen, oxygen, hydrogen atoms, how would you arrange them to get the lowest possible thermal conductivity? How would you arrange those atoms, and no fair using diamond, but how would you arrange those atoms to make the highest thermal conductivity? Right? what kind of physics could give us this thermal function? So what kind of physics could provide, a high contrast heat switch so that I don't know, I look at some material with, shine a flashlight on some material and its thermal conductivity changes. Or if I, put a magnetic field near it. Or, regulator, I'll explain what some of those things. So those are what I consider sort of problems. All right, so my first problem, and it has a long history, so my first problem is related to, how low can the thermal conductivity of a material be? And let me give you some background. So this, another way of looking at that is, can we get below the thermal conductivity of an amorphous arrangements of atoms? That was conventionally the wisdom of what the lowest thermal conductivity could be. If we destroy the order, we make a glass, the thermal conductivity is as low as it is possible. Can we do better than that? Right? And it goes back to Einstein, 1911, who described the heat transport as a random walk of thermal energy. Turns out Einstein's theory was wrong for crystals, and Debye pointed out the correct description based on phonons in 1914. But Einstein's original picture does work pretty well for glasses, and that's been kind of repeated over the years by a lot of different people. And the high temperature limit of this sort of picture from Einstein, as further developed by others, is basically this. This is what we call the minimum thermal conductivity, or amorphous limit of thermal conductivity. It's a numerical factor, K Boltzmann. I'm talking about heat. There better be K Boltzmann in the equation somewhere. N to the 2/3, that's the number of atoms to the 2/3 power per unit volume, and the average speeds of sound, longitudinal transverse, right? So basically no free parameters, you just plug it in and you go. All right. Well, okay, so what did Einstein originally do, right? And what really happened here? So this is the paper from 1911 that Einstein published. Essentially what Einstein was doing was building on his very successful heat capacity paper of 1907. So the Einstein heat capacity was the first work that introduced quantum mechanics to the solid state. But the thermal conductivity of that model is 0, because the Einstein oscillators are not connected to each other. They're isolated oscillators. So what Einstein did in 1911 is he coupled his Einstein oscillators together, and you can see he knew he was in trouble. He coupled each of the oscillators to 26 neighbors to try to get the heat conduction as large as he could, but it was still too small for a crystal, because he did not realize that phonons are the normal modes of a crystal. So next time you think you missed something that you thought should have been obvious, think about poor Einstein. He would have been the hero of heat transport as well as the hero of everything else if he would have gotten that right in 1911. Okay? Just a little word for the students. Don't do what he did unless you're Einstein. So what he did, he says his first sentence is in an earlier work, and then cites himself. Don't cite yourself first. That's not considered. But that's the Einstein heat capacity paper of 1907. So maybe it's okay. So it works very well. So this is the measured thermal conductivity. This is the calculated thermal conductivity, amorphous materials, disordered crystals, what we call strongly disordered crystals, including some very important technological things like stabilized zirconia, glass. Feldspar is the major component of the Earth's crust. So this kind of physics, is important, in a lot of things. Solid line is perfect agreement, and you think everything kind of works out pretty well. All right, so that's where that kind of was, a long time ago. And then, but in many attempts since then to try to do better. So find something with lower. And I won't go through all the details, I'll just skip ahead to the first one that was, successful in a kind of a bigger way at producing a thermal conductivity much smaller than this amorphous limit. And what we observed that is in a tungsten diselenide material, which was created by the modulated elemental reactance method. And what that means is instead of, think of it as like a nothing bad about this, but think of it as like a materials chemist version of MBE. So you deposit atoms on a cold substrate in the right order, in the right ratios, then anneal it to form the material that you want to form. So it's kind of a low temperature deposition followed by annealing. And what happens when you do it in this way is that you don't form, a crystal. What you form is a turbostratic layering of nanocrystals, essentially. So tungsten diselenide is one of these very popular dichalcogenide 2D layered materials. And so think of this material as, think about taking playing cards and throwing them down on a table. And if you put the playing cards together and don't put them into a deck, but leave the playing cards, rotated relative to each other, that's what this material is like. If you brought them all together into a playing card deck again, that would be the crystal. They'd be arranged in an ordered way. So this is a disordered stacking of these two-dimensional crystalline sheets. Okay, we do a lot of characterization to make sure that's all that what is. And what we found is that the thermal conductivity, of thin films of these materials, there's some variation, but let's just call it, 0.05, 0.06 watt per meter Kelvin near room temperature. That's about a factor of 2 larger than the thermal conductivity of air. It's about the same thermal conductivity as a styrofoam coffee cup material. But it's a fully dense solid, and that's the direction normal to this stacking. Here's a single crystal. That thermal conductivity is actually already pretty low. It's about, glasses here. But, this is, another factor. This is the minimum thermal conductivity, and then this was an irradiated sort of a reality check material. So the bottom line is, a factor of 6 or so below the amorphous limit for this material. So we get a material whose thermal conductivity is far below this kind of Einstein-like limit. Okay, well, what's going on? Well, there's a lot of things going on, it turns out, and there's a lot of missteps in sort of the understanding of this. Part of it is the fact that these materials are, of course, disordered. So the phonons scatter it, all the disorder involved in the material. Another aspect of the material that's important is they're strongly anisotropic. So that in terms of the elastic constants and the phonon velocities normal to the surface are much smaller than the phonon velocities parallel to the surface. That introduces something called phonon focusing, which is essentially a reduction in the density of states of the phonons that carry heat across the interface. And then only very recently we also realized, and that's what this slide is about, is that the shear modes are extremely softened in these materials. So think about these 2D layered materials. If the crystals are registered on top of each other as a crystal, then if I try to shear them, there's a corrugation and there's a restoring force. But if they're disordered, they're incommensurate, that corrugation is smeared out, and the restoring force for a shear motion is greatly suppressed, maybe. This experiment says, yes, that is true. So we did some experiments on a related material. This is moly diselenide with layers of tin selenide, which is a rock salt-like structure crystal. And we measured the shear modulus using surface acoustic waves. And the shear modulus is below 1 gigapascal, which is an incredibly small shear modulus for a solid. It's smaller than about the same as polystyrene polymer. This is a very soft thing, suppressed by a factor of an order of magnitude over the crystal. And that also suppresses the heat conduction. All right, this gives a little more technical detail about surface acoustic wave measurements because I'm about to use that to study polymers. I'm sort of changing gears a little bit to the organic world. This is just something that we worked on over the past several years. And it's kind of a convenient way of making a PDMS nanoscale mask. And we put that on we mold that in a silicon mold. We put that on a sample. This is just intended to show the optical intensities. If we bring light through the top, it gives the geometry. But essentially, the the point is we can do a pump probe measurement in our conventional optical measurement equipment. We can measure these oscillations in the time domain. We can get the velocity of the surface acoustic waves that travel across the surface, and we could extract elastic constants of materials this way in a quite convenient method, to complement some of our other techniques on longitudinal modes. And this just tells you that there's some optimization to do about how thick the layer, say if you want to measure the elastic constants of a polymer, this is just how do you optimize the thickness of the aluminum in order to get the best sensitivity to the elastic constants. And so, it just says, well, pick the aluminum thickness to be about 100 nanometers, and you can get a pretty decent measurement of the elastic constants of a polymer film. And we use these kind of things to design the experiments, and we go through to do that. Right? So this is just that. Okay, and the reason we needed that is we want to be able to relate some of the elastic properties of the materials to their thermal transport properties of materials. So again, this is maybe as a way of looking at how well can we use this Einstein-like picture for thermal conductivity, which was just predicated on speeds of sound, which was one of the inputs to that kind of model, to understand the thermal conductivity of soft materials. And can we find materials that have thermal conductivity much lower than what might be predicted by that kind of model? So this is just a systematic variation in bonding as we go through materials that are mostly van der Waals bonded, through materials, polymeric materials that are hydrogen bonded, all the way to these somewhat exotic, you might call them ionic polymers or ionic polymer salts, where the chains are bonded by relatively strong ionic interactions. Right? So we go through this, and that increases the strength. So we can vary all these things. This postdoc that was working with me on this, I think he ended up measuring and reporting in the literature thermal conductivity elastic constants for almost 30 polymers, over a couple different, 2 different papers. This gives an example. This is just from that particular data set. We go all the way from polystyrene. This is the C11 modulus. That's the longitudinal modulus. That tells me how a longitudinal sound wave propagates. And C44 is the shear modulus. That tells me how a transverse sound wave propagates in the materials. And these are the things, these are the measured values for all these different films, going from van der Waals bonded polystyrene to ionically bonded, this ionic salt, polymer salt material. And it spans almost a factor of 20, or 10 or so in elastic constants. So we can vary the elastic constants of the polymer by about a factor of 10. And if I organize the thermal conductivity we measured for these materials versus that speed of sound in the materials, we should get something like a factor of 3 range, square root of 10, and that's basically what we see. So everything kind of works pretty well. The minimum thermal conductivity model would just predict a straight line going through the origin. All these polystyrene is a little bit below that, but as we go here, something a little kind of turns up a little bit. But the maximum we get is about 0.6 watt per meter Kelvin for these kinds of amorphous polymers. Actually, we're still working on this kind of thing. I have a little bit of money from a company that makes, believe it or not, coatings for magnet wire. And they would love if the thermal conductivity of their magnet wire coating was a little higher. And you might think this is, okay, it seems a little funny, but imagine how important this is really. That if you can make electrical motors that can dissipate their heat better, this makes the motor smaller, it makes it, the weight less, on and on and on, right? And it turns out to be a really very significant, problem. All right, so that just sort of, again, confirmed the Einstein picture. Let me go farther. I'd love to talk, great that I can talk about this at Rice. So here's C60, our friend. This is PCBM, which is C60, which is functionalized with a small organic ligand, which makes it soluble in polymers. It's been developed for organic photovoltaic applications, organic electronic locations. This is just a different one, has a little different extra, molecular weight there. And there was a report, very, very low thermal conductivities quantities of materials, which we were not able to reproduce. I suspect there was little problems with the characterization of thicknesses and things like that. But we found certainly very low thermal conductivities, also very comparable to the tungsten diselenide in basically these classes of materials, these functionalized fullerene derivatives, right? And this is kind of just a summary, one summary of some of that data. So if I plot the heat capacity of the layer, which we measure, and the thermal conductivity of a layer on the same plot, these circles are confidence intervals. So we have two parameters, so it turns out they're coupled in complicated ways. So think of it as a two-dimensional error bar. The best fit to the data is the middle of that error bar, and then these circles give you something like 95% confidence that the thermal conductivity and heat capacity are inside that circle. Doesn't include systematic errors. If you're a measurement geek, then you worry about all these things all the time. This turns out just to be random errors. It doesn't include systematic errors, and anyway. But okay, it gives you a good idea of what's going on. This is PMMA, a typical polymer. This is C60, the fullerene film assembled from the fullerene. This is a whole variety of different types of fullerene derivatives deposited in different ways, and actually this is just a couple of them, but we did 10 or something. And they're all very similar, they're all about this 0.05. So the bottom line is the heat capacity doesn't change very much, but the thermal conductivity goes down. And what's so curious about all this is that in some sense you might think this material should look something like the mixture of C60 with a polymer. And that would be the effective medium way of thinking about the material. I mix a polymer and fullerene, and I get something in between. But if I mix a polymer and and C60, I don't get in between. I get lower, and I get incredibly low. So this is again the kind of lowest thermal conductivity of any dense material that we know about. Created by that kind of mixing. All right, I'm going to take okay, I got enough time. Probably don't. I'm going to skip the magnons. Okay, let me talk about thermally functional materials. So the motivation here is, to create maybe more engineering application in thermals, or more flexibility, say, in thermal management. Be able to bring materials to engineering design that could do something for us in a thermal management system. So I can think about different kinds of function. We can think about, I think about passive function. So say a thermal regulator. I think of a thermal regulator ideally as something where the thermal conductivity is low at low temperatures and then becomes high as I make the temperature higher. So if something's generating heat, it would get up to some temperature, maybe operating temperature, and then it wouldn't heat up anymore. So think of that as the thermal analog of a voltage regulator. A voltage regulator says I put any voltage on it and I can, it'll drop the voltage to some particular thing. This would be I put any heat current through it and I would end up at the same temperature. So that would be a thermal regulator. Another kind of thing that's a lot discussed is if I can combine materials that have a steep increase in thermal conductivity with a material that has a steep decrease in thermal conductivity, then I can make heat flow easier in one way than the other by combining these two materials. So I just put one on one side and the other, and I break the symmetry of the problem, and so heat will flow more easily in one way or the other. Also would be a wonderful thing, right? Imagine the wall of your house could behave like that, and when it's hot outside, I don't know, it's insulated, but when it's cold outside, it heats up or something, this kind of thing. Anyway, whole other category is an active function. So we think of a thermal switch. So something where I say I flip a switch and its thermal conductivity goes from low to high. Heat dissipating to heat insulating. right, where we're, okay. And I'm talking about, I put it in the category of materials discovery. So I want to discover materials with new physics that will provide new function. There's an absolutely valid way, which is also going on here, which is to engineer kind of systems that involve mechanical components maybe that can create contacts and take them apart and things like that. And that's perfectly valid, it's just not what I do. So we want to discover materials with new function or improve performance, and we use, our measurement techniques. We're good at that. We can very efficiently, explore a lot of materials and a lot of systems, and I'll give a bunch of examples. We have a lot of people at Illinois. It's a huge materials community, so we have lots of people to work with, on all kinds of different kinds of systems, and that's been very productive. All right, where does this kind of go back? So passive control, thermal regulator. So I want a material that has a low thermal conductivity and then increases to a higher thermal conductivity. Well, there's a well-known class of materials which are called, insulator to metal transition materials. Vanadium dioxide is the kind of the most studied, most famous of these materials. It goes from a really good electrical insulator to a metal, but not a very good metal, at a very abrupt temperature around 360 Kelvin or so. So there are a lot of these kinds of systems. They transition between an insulator and what I would call a correlated electron metal. So they have quite high resistivities in the metallic state. If I apply the Wiedemann-Franz law to that conductivity, I would get 2 watts per meter Kelvin. So that's just, taking the Lorentz number, multiplying by temperature, you get that value. So you get a number which is quite small. 2 watt per meter Kelvin is not a very big thermal conductivity. I already talked a lot about minimum thermal conductivity of phonons. In these kinds of materials, that's typically on the order of 1. So really, even if I made this material as good as I could make it, I probably can't get a contrast better than 3. In other words, I have 1 watt per meter Kelvin, the thermal conductivity increases by 2 to 3 watt per meter Kelvin at higher temperatures, due to the electrons turning on. Right? Well, it turns out we were never able to see anything that big. We worked actually really hard on this with a group at Toyota, and Toyota Research Institute of North America, and the best we could ever get was still less than 2. So, but that was kind of the best we could do. Fast forwarding, this is the best, I would say the best thermal regulator material we have so far, that we've been able to come up with in the group. And this is a shape memory alloy. It's a ferromagnetic shape memory alloy. It's actually a known material. It's very sensitive to this composition of indium. It can also be done with tin. And it's been used in lots of, in other kinds of science. This is what we measured. So this is the thermal conductivity of this material. At room temperature, we tuned this composition to make that change occur near room temperature. And it's a little bit better than a factor of 2. So the thermal conductivity increases by about a factor of 2 at a phase transition. It's a Martensitic transformation, a martensite, an austenite phase. At this temperature. If we measure the electrical conductivity and use the Wiedemann-Franz law, the electrical conductivity you can see is basically most of that change. So the lattice vibrations don't seem to play much of a role. The electronic heat conduction increases at the transition and produces most of that change. It's a complicated material. This is a TM image of the room temperature martensite phase. There's all kinds of kind of nanoscale twinning and stuff going on in there. We're really not sure what that does exactly to the transport properties. We measured the electronic mobility and the sort of the effective carrier densities using Hall effect measurements. This is not so easy because the materials are magnetic, and so there's anomalous Hall effects involved. But okay, I have some people that know more about this than I do, and they were able to extract that the mobility increases almost a factor of 3 at the transition, while the effective carrier density drops a little bit, and that kind of explains the properties of the material. So can we find other materials that have a bigger change in mobility or carrier density? Well, we don't know. Where would we look? It's hard to find guidance, actually. Where would we find this material? Where there's nothing stopping the at the transition between different phases that the mobility could change by an order of magnitude. But where would we find it? So that's the kind of problem that we're at there. Okay, active control. So something that we can switch, and I'll finish with this. This is one example that goes back some years. I guess that's this paper, 2014. Other groups have done this too. This is one of our papers too. This is from Stanford, where electrochemical systems, you could put, intercalate lithium, take lithium out, you basically charge and discharge a battery, and its thermal conductivity changes. So here's the thermal conductivity of a lithium cobalt oxide as a typical, cathode material in a lithium ion system, where the thermal conductivity drops from 5.4 to 3.6, as you charge and discharge the battery. It turns out this is this paper has actually gotten a lot of renewed attention right now because people actually care about what's happening to the thermal conductivity inside a battery when you charge it and discharge it. Because if you want to charge a battery really fast, you want to pull up to a filling station and do the equivalent of pumping gasoline into your tank, but doing it with electrical current, in 10 minutes or something, so you can go to the bathroom and get a cup of coffee and your car's charged. It turns out the thermal issues are really severe. And every bit matters, in terms of what the thermal transport is in the system. Okay, but we were thinking of this sort of switching process. We can change the thermal conductivity, but you can see it's slow. It takes a long time to charge a battery. It takes a long time to discharge a battery. So maybe, practically speaking, maybe it's not so great. All right. Here's something that's extremely fast. Right? This is ferromagnetic system. It's what we would call a synthetic antiferromagnet. It's made from layers of cobalt separated with spacers of copper. You can see the space. This is true nanoscale, 3 nanometer, 1 nanometer. Stack it up many times, 39 times, make this multi-layer. What happens is that the magnetic order of the cobalt layers is anti-parallel in zero field, and at a very modest field, a couple hundred Gauss, then the magnetic moments become aligned. So this is the same as GMR, so giant magnetoresistance, if you're familiar with that, but it's just the thermal analog of it. So this is actually the GMR is this red curve is the GMR. This is the thermal GMR. This means transport perpendicular to the plane. And the thermal conductivity again changes by about a factor of 2 with the application of a magnetic field in this material. And like I said, this in principle is extremely fast. It's really whatever the speed is of that switching, and that switching is related to things like ferromagnetic resonance, and that's gigahertz. So sub-nanosecond, kind of problems. Here's one from the soft matter world, right? So we had sort of metals and maybe sort of more like electronic materials, maybe magnetics. Here's one from soft. Here's an example where we took this was designed by the student, Jungwoo Shin, very impressive guy. He's doing a postdoc at MIT right now. He designed this whole system. It's a polymer with this side chain that has this azo group on it. This group functionality here is when you shine UV light on it, it transforms to a different isomer, which is no longer flat. So this flat system turns into this buckled system, and that changes how the chains are packed. And I want to just point out that there's a group at Tokyo Tech that did something very similar before us, though it's actually related to an interface, not to a bulk crystal, but a similar idea. Also measure thermal transport. And this is what happens. So if you shine, this is visible light on the material, you get the flat isomer. That material can crystallize. If you shine UV light, it basically melts. When the polymer becomes buckled, it doesn't pack as well. And when that happens, the thermal conductivity, this is the cis configuration, this is the trans at different temperatures. At high temperatures, they're the same because they're both melted. At lower temperatures, you still get a liquid, then a glass. And in the trans state, you get essentially a crystallized material or partially crystallized material. And if you sit in your room temperature and go back and forth with light, the thermal conductivity changes by almost a factor of 3. And it does it on a time scale of seconds, tens of seconds, something like that. So here is a light-activated thermal switch. Hard to imagine exactly where you would use that. Where would you shine light on something that you'd want to change its thermal conductivity? But, you know, in terms of the proof of principle, the design of molecules, the design of materials that have the kind of functions that we're looking for, I think this is a wonderful example. All right, so let me just conclude there. I would say there's a lot of, I hope I've left you with the idea there are a lot of compelling puzzles. I've emphasized problems in the field of thermal transport. Maybe the main point is that the conventional wisdom on the lower limit to the thermal conductivity based on this kind of minimum model was wrong. And we really have a kind of race to the bottom, both in inorganic, organic materials. Not clear where we should look. That was one of the things that I brought up about problems. Maybe we're not really sure what the solution is or what we would do next. And I would say many materials could potentially provide thermal regulating, thermal function. We certainly would like to find materials with higher contrasts. You know, could there be an application? It turns out we worked with the Toyota group also on that shape memory alloy, and they filed a patent on it. I don't know that it's particularly practical, but they wanted to protect the idea. And the idea is that you would have a material where you're operating, say, a battery, and it would be somewhat thermally insulated. It would heat up better, you know, to get to an operating point. The material's thermal conductivity would go up, and then the battery's thermal temperature would be managed, right? And so, you know, where do you find things like that, both materials, applications, that could kind of move the field forward? So, thanks.
Okay. So thanks, David, for a fascinating talk, and I'm pretty sure that those are problems that actually departments, students, and faculty would like to address. So with that, any ideas? Please go to David. Yes, please.
You know, in the amorphous tungsten selenide that you talked about, the stacking, is it still Van der Waals type of? If that is the case between the crystalline, which is also Van der Waals stacking, why should there be that much of a big difference in the thermal conductivity?
Yeah, I mean, that's a good point. I mean, you know, in the crystal also has the anisotropy is also present in the crystal. I would say the anisotropy in the crystal is, at least for the shear modes, is not anywhere near as strong as it is in the disordered mode. So that was one of the things I was emphasizing, that if I have this disorder, you know, the shear velocities are greatly suppressed. And so transport of shear-like vibrational modes, that direction is very poor, inefficient. So that's one thing. The other is just the disorder. So acoustic phonons in the crystal, you know, it sees a periodic lattice, so block waves, they just transport. They're only scattered by other atomicity.